sensor. Okay, so normally for temperature measurement, temperature of a given material changes, it increases or decreases when heat energy is gained or lost by it. For temperature measurement in the laboratory, normally we use a thermometer, and thermometry is based on the conversion of variation of some physical property into the temperature variation of the metal. Okay, you know about the platinum resistance thermometer. All the metals, when they are heated, their resistance increases with increase in temperature. RT is equal to R0 1 plus alpha T. So variation of electrical resistance of high purity platinum wire is converted into temperature variation. The platinum resistor has a nominal resistance of 100 ohm at 0 degree centigrade, and then it changes by 0.4 degree per degree centigrade. You can see from here we have a longer range for platinum. All other metals also behave in the same way, but since platinum covers a larger range of temperature, that is why we use platinum resistance thermometer. So in this experiment, platinum resistance thermometer has been used as a standard. Okay, in the previous lecture we talked about thermocouple. That means if you take two dissimilar materials, join them together, put one end at the cold and the other end at hot, some thermo EMF gets generated. This is called Seebeck effect. Okay, so this is the same thing. In fact, we have already discussed in the previous lecture about thermocouple. This is Seebeck effect. Okay, so in this case, two junctions are made of two dissimilar materials, copper and constantons. In the previous experiment also, we have used the same copper constantan thermocouple. When the two junctions are temperature T1 and T2, and thermo EMF appears, and this thermo EMF is not a linear function of time. Okay, in fact, if you plot T as a function of temperature, it comes out to be, you plot a thermo EMF here, and the temperature here, it shows a behavior like this. Okay, the temperature, this is called a neutral temperature, and this is called the temperature of inversion. Okay, you will be doing one experiment where you are going to study even the temperature of inversion and neutral temperature also, but that experiment has been set up by Professor P.T. Ramesh. He will discuss about all these things. So we can write down this equation E. E is normally equal to A plus B T plus C B square. We can fit a polynomial to this one. Okay, so we have to, just with the help of this experiment, we have to understand how copper constantan thermocouple and a forward bias PN junction diode can be used as a temperature sensor. It's a very simple experiment. So here the value of thermo EMF versus T1 when T2 is held constant is a curve, okay, and that is a polynomial. It is A plus BT plus CT square. The slope of this curve at any temperature gives the thermoelectric power, and thermoelectric power also we talked about for copper constantan thermocouple. It's the 40 microvolt per second. In the previous experiment of thermal conductivity of copper and thermal conductivity of perspex, the voltage difference measured by the thermocouple was converted into the corresponding temperature difference by using this thermo power of 40 microvolt per degree centigrade. Since thermo EMF is small, so we have to amplify it by using DC difference amplifier in the same way that we discussed in the first lecture. Okay. The other is, if you take a PN junction diode, okay, PN junction diode is forward biased. If you take a forward biased PN junction diode, allow a very small amount of current to pass through it, and now you heat it. The forward bias voltage decreases with increase in temperature over a limited temperature range. Okay, so we have a forward bias PN junction. We allow a current of 1 to 2 milliampere to pass through it, and now we heat it. And we measure the forward bias voltage, and this forward bias voltage decreases linearly with temperature. Okay, and diode thermometer, this property of diode can be used to just measure the temperature by using diode thermometer. This is the underlying theory. We can write down the diode equation. It's a well-known equation. I is equal to IS e to the power QP over KT minus 1. We can approximate this to be, this 1 is much smaller than this exponential term. So we can write it like this. IS here is the saturation current, So from this equation we can write down the voltage V to be equal to kT over K ln of I minus IS. In our forward bias junction we are fixing the current I, so we differentiate this equation. So if you differentiate this dV over dt, we are differentiating with respect to the temperature. So we have a temperature here and we have a temperature here also, because IS, reverse saturation current, is also a function of time. Capital I, the current through the diode, is constant. So we differentiate, this is the first term and this is the second term, that is the differentiation of a natural log of saturation current. I in our case is constant. We can write it like this. Now saturation current goes as some constant T square e to the power minus Eg over kT. Eg is the band gap. So we take the log of this, we substitute it here. Okay, so finally we get the value of dV over dt as V over T minus 2K over Q minus Eg over T. If we substitute the data for silicon, okay, so we get the value of dV over dt to be equal to minus 2.2 millivolts per Kelvin. So normally for a silicon diode, if we fix a current, the change in voltage as a function of temperature, or that is the decrease in voltage as a function of temperature, for every degree centigrade rise in temperature will be just 2.2 millivolts. So this fact can be used to calibrate silicon diode with a fixed current passing through it in forward biasing condition as a temperature sensor. So here in this case we need a regulated power supply, we need a temperature controller, we need a furnace, we need a constant current source, we have an insert containing diode and copper cross-reactance thermocouple, we have a DC differential amplifier, and we have two digital multimeter in the 200 millivolts range. This is the furnace. So in the furnace, this is a tubular furnace. Okay, we have basically this ceramic tube, which is a hollow cylinder. It's open at both the ends. Nichrome wire of about 10 ohms is wound on to the middle portion of this inside. The tube is put inside a cylindrical. This is an aluminum box. This is how the furnace looks like. Okay, and it is the inside of this is filled with glass wool surrounding the ceramic tube to provide thermal insulation. The furnace can reach a temperature of 300 degrees centigrade when powered by a regulated power supply. These are the connection for the regulated power supply. When the furnace is heated, the two ends must be loosely plugged with a bag of cotton. So we fill some cotton here. This prevents the convection current taking away the heat. Finally, when we have to cool down, we have to take out that cotton so that it cools easily. Okay, we have so inside this we have an insert. Insert is nothing but a copper block. Okay, and on one side we have a diode here, and here we have a platinum resistance thermometer, and we have two terminals of a copper cross-linked thermocouple. Okay, it is inserted in this furnace. This is the furnace. So we insert it. This is basically a support, and it goes inside. It gets heated, and we make the measurement for both the experiments. Then for temperature thing, okay, we have a temperature controller here. This temperature controller is press button. You just press it and set the desired temperature. It contains a relay inside, which is closed normally, and the temperature oscillates. If you set a temperature, the temperature oscillates to plus minus half degree centigrade. So for doing the experiment, it's very simple. You have to connect a stabilized power supply through the relay of the temperature controller to the furnace. So this is for heating the furnace. The furnace has an insert which is suspended through it from a terminal disc at the stand. Okay, it goes through the ceramic tube inside. The insert is a long aluminum rod, 1 centimeter by 1 centimeter, with an axial hole of 3 millimeter diameter. Platinum sensor is there onto this block. One junction of copper cross-linked thermocouple is also there onto the same aluminum block. The other junction is inside the copper tube. This is fitted to the terminal block, okay, which the insert hangs inside the furnace. These are all lying on inside the lab. Some of the inserts are there, okay, they are lying outside. You can see also it's a simply aluminum block on which all these things are fixed. We have to do, in fact, you have to do 3 experiments using furnace, and this is one experiment that you have to do. The other experiment is PCR of copper and energy band gap of silicon, and the third is the verification of Curie bias law. These are the 3 furnace experiments you have to do. Okay, and so the silicon diode is also fixed onto the same stabilized power supply is connected to the relay. The relay will close. If you set a temperature, the relay will close after that. A platinum 100 thermometers is also fixed. Okay, forward biasing. So what we do is we set a current of 1 or 2 milliampere through a forward bias PN junction diode. Okay, we measure the forward bias voltage across the 2 ends of a silicon diode by using a digital multimeter in 2 volts range. We measure it starting from room temperature to 100 degrees centigrade. The precaution that we have to take that we have to increase the regulated power supply voltage in such a way so that the change in temperature is slow. It should be around 1 to 1.5 degree per minute. This is a common precaution that we have to make in all the 3 furnace experiments, that we have to increase the voltage from 7.5 volt to 12.5 volts in such a way so that the change in temperature is not more than 1 to 1.5 degrees centigrade per minute. So we have to increase the applied voltage slowly to maintain the state of heating. Okay, and maximum of around 12 volts is needed to get a temperature of 120. So we have to record the forward bias voltage with a fixed current passing through a PN junction diode as a function of temperature. Okay, we plot a graph. Unfortunately, the graph is not coming here. So if you fit now a graph to the data, it comes out to be, okay, this is a graph. Okay, we have a forward voltage V across the diode, and this is the temperature. So you fit a graph here. Okay, so V is equal to, you can check from here that for every 1 degree change, because if the value of T is 1 degree, the change is minus 0.0021. So that is roughly 2.1 millivolts, because readings are in volts. So it confirms the theory also that I showed you earlier. So from here, what we have to do, we have to calculate the value of P. If you are working in origin, you can find out the standard deviation directly. Otherwise, on actual state, you can find from this, you can calculate the value. So this is the equation of the fit. This is the equation of a fit, same value. The standard deviation, we can find out. Standard deviation is square root of difference between the measured value and the calculated value, because we have a data where we have measured this V as a function of T. Now we are going to fit a graph between V and T. By using this, taking T as a variable, we can find out the calculated value. We take the difference between the calculated value and the measured value, and from there we can find out the standard deviation. It comes out to be plus minus 1 volt. In fact, we had a table here, but that is not seen. That has basically, it's given in the manual also. So that table shows how can we calculate the standard deviation from the given reading. Okay, it is under root of, that is square root of difference between the measured value and the calculated value. Okay, so standard deviation comes out to be plus minus 1 millivolt. Since the diode voltage changes by 2.11 millivolts for every degree temperature change, this standard deviation will correspond to an error of 1 millivolt here, and this is 2.11. So if you calculate this, it corresponds to an error of 0.5 or half degree centigrade. So with this calibration graph, we can measure the temperature with the silicon diode. The other is thermocouple calculation. We have to do the same thing. In fact, we have to perform both the experiments simultaneously, because both the thermocouple and the junction diode, they are there onto a aluminum block. They are inside. You are heating in the same furnace. So you have to record again, connect I1 of DC differential amplifier, and we have to measure V plus and V minus of a thermocouple, because thermo EMF we have to measure, because we have to amplify it by 100 times. We have to set a temperature to 160 degrees centigrade. Okay, this is the upper temperature. Temperature will not cross this, but you can limit to 120 degrees centigrade as we discussed earlier. So we have to switch on this DMM. You know about differential amplifier. Okay, so we connect the two ends of a copper constant thermocouple to one terminal of a DC differential amplifier, and by using a digital multimeter in DC 200 millivolts, we measure the voltage as a function of temperature. Okay, and again we do the same thing. That means we have to regulate the voltage in such a way so that the temperature of a furnace rises 1 degree centigrade or 1.5 degree centigrade for every minute. Okay. Then again, if you plot a graph, here in this case we have thermo EMF. It is again both the readings B plus and B minus. So B plus minus B minus divided by 2 is here. We have a temperature here. If you plot a graph and fit a polynomial, A is equal to, so polynomial B is minus 1.068 plus this into T plus this one. Again, if we put the value of T as 1, we can find out from here that if we change the value of T by 1 degree centigrade, the change in thermo EMF is 0.0378 volt. Okay. So this is a second degree polynomial fit to the data. So B is equal to this one. Standard deviation we can calculate the same way. Okay, you put the value of T that you have used for the temperature. You find out the measured value by using this fit. Find out the difference between the measured value and the standard value. Take the square, add all the readings, take the square root and divide it by n minus 1. That is the definition of standard deviation. It's also given in the manual. So standard deviation comes out to be 16 microvolt. Again, this 16 microvolt and 37.8. So it gives us a temperature of the same order. That means in the case of silicon diode, we got the accuracy of 0.5 degree centigrade, but here we are getting 0.25. We can also find out the thermoelectric power. If you differentiate this, V is equal to, so it is dB over dt. So dB over dt gives us this. So this gives us a thermoelectric power 40 microvolts per second. We discussed about copper constant thermocouple. So this experiment will give us a feeling that we can make use of copper constant thermocouple and diode in forward bias diode by allowing some current to pass through as a temperature sensor. Okay, so it's a very simple experiment as compared to the previous experiment that we discussed. So this is all about this experiment. Any question? So you have to see, you have to read about the furnace, because tomorrow morning we have to discuss another experiment which is similar to the furnace. So by using furnace, you are going to perform 3 experiments. One is this experiment, calibration of copper constant thermocouple and diode as a sensor. The second experiment that we will discuss tomorrow, it is temperature coefficient of resistance of copper and energy band gap of silicon. Energy band gap of silicon is very interesting experiment. You can take a small chip and measure its band gap. And the third experiment is verification of QB bias law. Okay, you can take a ceramic capacitor and measure its capacitance by using